Oh, okay, that makes sense. Okay.
All right.
Yeah.
So the big news, well, there's a quiz today. That's not such big news. But then Tuesday is exam 1. I don't have anything like that. I'll think about whether I can do that. But well, I'll give you all the formulas that you need, like in the back. Okay, so Tuesday, and the problems are going to be similar to like the ones in the introduction and the first law of thermodynamics. And I'm planning on today being mostly just review. We'll see how far we get. If we get through the stuff that I was planning to do today for the review, then there's a couple of more things that we can talk about that won't be on the test. But so let's do this. If anyone has any homework questions, we'll do that first. And then I want to go through what to me is kind of a review of the equations. In a way, it's not like a list of equations or whatever, but to me, it's sort of the way to think about the equations that we've talked about. And then I have a couple of problems that I'd like you to work on together, and after you have a little time to work on it, I can go through it. And so that's sort of the format I'm thinking of for this review. First, anybody have any homework questions? Yeah. Yes. From the first one. Oh, first law, yeah. Yeah, I was sort of expecting to get 8 or 10 or both. They both use that linearity of the spring thing. So the idea of this one, oh, this isn't the one with the spring. This is the one that just says pressure varies linearly. Can I look? Do you have the problem in front of you? Okay, so we have a piston cylinder. And it expands from a volume of 0.3 meters cubed to 1.5 meters, so it's expanding. At this first instant, so at instant 1, the pressure is 2.0 times 10 to the 5 pascals, and the volume is 0.3 meters cubed, and then it goes to a later pressure of 0.5 times 10 to the 5, and a later volume of 1.5 meters cubed. And we're told that at equilibrium, the pressure varies linearly with the volume. So we can write this as pressure is equal to A plus B V. And we're going to assume that this expansion happens quasi-statically or in quasi equilibrium. Those mean the same thing. Quasi equilibrium means that this expansion or whatever process you're dealing with is happening slowly enough that it's like there's equilibrium at every point. And you can, whatever rules hold for equilibrium, you can assume they hold as this process takes place through the whole process. So we're going to assume that pressure is going to, through this process, vary linearly. And we are trying to find a work. Okay. So to calculate the work is equal to the integral of P dV from volume 1 to volume 2. And anytime you see this equation, what you should think is, okay, I need to find pressure as a function of volume. In order to do that integration, well, you know, if pressure is constant, then you can do it right away. But normally, you're going to have to find, so I need pressure as a function of volume. Okay, so, well, we have this linear relationship that happens because we're assuming quasi-equilibrium. And we have these two states. At instant 1, we know the pressure and volume. Instant 2, we know the pressure and volume. So we can set this up as at a volume of 0.3 meters cubed. The pressure is equal to 2.0 times 10 to the 5th pascals. And at a volume of 1.5 meters cubed, the pressure is 0.5 times 10 to the 5 pascals. And that's just going to let us set up a system of two equations for two variables. So this will be our first equation. This will be our second equation. Our first equation says, so if you look at this linear function, the pressure of 2 times 10 to the 5th is equal to A plus B times 0.3. Okay. And the second equation is going to say 0.5 times 10 to the 5th is equal to A plus B times 1.5. That's going to be two equations for two unknowns. So the first one says 2.0 times 10 to the 5th is equal to A plus 0.3 B. And the second one says 0.5 times 10 to the 5th is equal to A plus 1.5 B. The people who took statics with me, you know, we've solved a billion, maybe not a billion, that's a lot, but systems of equations. Yeah. It definitely rounds up to a billion, yeah. So on your graphing calculator, you can just solve that using reduced row echelon form, but this is 2 and 2. It's easy to solve by hand, just do it by substitution or whatever. But when you solve this system of equations, anybody want to do it right now while we wait? Okay. Okay, thanks. Okay, so what we know is that pressure is a function of volume is equal to the integral. The volumes go from 0.3 to 1.5. I'm getting ahead of myself. That's not the pressure. The pressure is 2.375 times 10 to the fifth minus 1.25 times 10 to the fifth times the volume. And so the work is the integral from a volume of 0.3 to a volume of 1.5 of 2.375 times 10 to the 5 minus 1.25 times 10 to the 5 V, and we're integrating that with respect to volume. And so that's 2.375 times 10 to the 5 V minus 0.625 V squared, evaluated from 0.3 to 1.5. And can someone calculate that? 1.5 times 10 to the fifth. And we did everything in SI units, so the units are joules. Yes. That's still the answer, though, right? Okay. Okay, and then the last question is, does the sign of the work make sense? Yes, the gas is expanding, so it always does positive work. Any questions about that one? Problem 10 is a little more complicated, but you use the same idea for using the linearity of the force applied by the spring. You set up the equation for a line, and then you use the boundary conditions at the two ends of the process to come up with your two equations for two variables for the line. It lets you solve for the constant and the slope, the thing that's not a constant. Any questions about that one? Any other homework questions? Yes. Yes. Sure. Anybody have the heat problems? Heat? Okay, so we're talking about the cover for a grill, and the outer surface has a temperature of 47 degrees Celsius, and the emissivity, that's the epsilon in the radiation equation, is 0.93. And the heat transfer coefficient for convection, that's the H in the convection formula, between the hood and the surroundings at 27 degrees Celsius is 10 watts per meter squared. What's the net rate of heat transfer between drill hood and the surroundings by convection and radiation? In watts per meter squared of surface area. We need dimensions for that. Are there no dimensions? Well, that's part of the problem. So let's say that the hood, this just in. The hood has a surface area of, what, half a meter squared? Oh, that's a good idea. That's sophisticated. Let's just do it for this area. Okay, so the total heat is the heat from radiation plus the heat from convection. And we're talking about rates of heat transfer, so we'll do all of those dot. So heat due to radiation. This is radiation emitted, and that's equal to the emissivity, so 0.93, times the Stefan-Boltzmann constant, 5.67 times 10 to the minus 8, I think. And then times the Kelvin temperature of the body to the 4th power. So the Kelvin temperature, Celsius temperature is 47, so the Kelvin temperature is 47 plus 273.15, the 4th power. And what do you get for that? $320 watts. Okay.
Oh, yeah, yeah, yeah.
For the what?
Sorry, I'm sorry.
That's the whole thing?
That was just the temperature.
Okay. Oh, yeah. Can someone multiply it all together? Yeah, we have a times 10 to the minus 8 in there.
We need the surface area.
Yes, I left that out, didn't I? Sorry. Okay. So there's also a 0.5 for the surface area. And then this is 320.15 to the fourth. And what do you get if you multiply all that together? Huh. And that's in watts. Yeah. Mm-hmm.
Okay, so you said that the model for something, a smaller body radiating in a much larger surrounding area was the temperature of the body to the fourth minus the temperature of the surrounding area.
That's right.
Why does it not count in this case?
Yeah, actually, so my thinking on that is that there's no body outside of it radiating, I mean, but there's the sun out there radiating. There's the atmosphere that I suppose radiates. So that, actually, that's probably something I should look into and get back to you on. But so my thinking on that is we're just worried about the emission of heat by this body.
Well, I guess what I was thinking of as being the external body was just the surrounding air.
The surrounding air, yeah. I need to get back to you on that. I don't know. Yep. I don't know. I've never done anything like that. But so the way you did it was you use this formula with a surround with a body at 320 degrees and then a surrounding body at 27 degrees Celsius. Yeah. Mm-hmm. Yeah. Yeah. I promise I'll be clear about that on test problems, whether I'm talking about a net radiation or an emitted radiation. But for now, let's do it this way, and I'll find out about that. And then we have to do heat convection. So this is equal to H times A times the temperature of the body minus the temperature of the surroundings. And we're given the constant H is equal to, 10. And the area is 0.5. And then the difference between these two temperatures, 47 minus 27, so 20. And we get a total rate of convection of 100. And now we have to think about the signs. So you can think of this as, this is emitted. But, yes? For what? Well, convection always depends on the difference between the thing that's the body that you're looking at and the fluid that's taking the heat away. And so there's no, well, radiation, there are two ways we've talked about radiation. One is just pure radiation emitted from a hot body. And the second one is a net radiation when a body is surrounded by another body. And so it depends which one of those you're talking about. Well, it just said, yeah, I didn't write it down here. It said convection, the constant of convection was this at 27 degrees Celsius. The body's 47, but I don't think I wrote the, but the idea is that the surrounding air is 27 degrees Celsius. Now we have to think about the signs. So these both give rates of heat that are emitted. Our chosen body is the, so we're trying to figure out, you know, if our system is the hood, then positive heat is heat coming into the hood. And so the total Q dot for the hood is equal to 276.98 plus 100. No, you have to change the signs. That was the whole point of this. So negative 376.98 watts. So if we did it as net radiation between hood and 27 degrees Celsius surroundings, then that Q dot emitted by radiation would be 0.93 times 5.67 times 10 to the minus 8 times the cross-sectional area times 320.15 to the fourth minus 300.15 to the fourth. And can someone tell me what that is? $62.99 watts. And so then, in that case, the net heat, the energy acquired by the hood through heat would be negative 62.99 minus 100, so negative 162.99 watts.
That what would be accounted for by the net radiation is maybe instead accounted for by the convection. See what I mean?
I do see what you mean. Let me find out for sure, and just I'll tell you next time. But on the test, I'll be very clear about whether we're talking about a net radiation or just a radiation emitted. Okay. Any questions about that one? Yes. What? Well, it's one of two possibilities. Depending on whether we're talking about net radiation. If it's net radiation and we're treating the surroundings, the atmosphere, as a surrounding body with a temperature of 27 degrees Celsius, it's this. The more I think about it, the more I bet that's the way you're supposed to do it. But if we're just talking about radiation emitted, it's this. But I'll find out. Any other homework questions you want to see? Number one, sure. From heat. What? Are you going to post the answers for heat? I guess now I'm probably not, since I'm doing them here. I don't know, maybe. Okay, so now we're talking about a wall made of concrete. That is a really screwed up wall. Fix that. Okay, so there's the wall. And it has a thickness of 0.2 meters. And the area of the face is 1 meter squared. The coefficient of conductivity that's kappa, and that's equal to 0.5 watts per meters Kelvin. And the total conduction is 0.15 kilowatts. We're going to assume that the temperature of the wall varies linearly as you go through that thickness. And what we want to figure out is what's the difference in temperature between the inside of that wall and the outside of the wall. So the equation that we're going to use is that the rate of heat emitted is negative coefficient of conduction times the area of, think of that area as like the window that the flow is through, cross-sectional area, times the difference in temperature. So I'll write that as delta T. So then this is equal to negative 0.5 times 1 times delta t the total rate of conduction is 0.15 times 10 to the third watts. And so I guess that just gives you that the temperature difference is negative 0.30 times 10 to the third. Kelvin or Celsius. So 300 degrees. We never had to use that linear variation, but that's all you have to do in that one. Yep.
Does the linear variation come in to the equation from negative kappa a dt over dx?
Oh, is my formula wrong?
Well,
yeah, okay, yes, my formula was wrong. Thank you. So this shouldn't be a change. Sorry about that. This shouldn't be a change in temperature. This should be the derivative of the temperature with respect to like the distance through the wall. Okay, so now we're going to use that linear relationship. So let's think of, let's come up with temperature as a function of x, okay? And we'll say like the temperature is equal to a plus bx. Then dt dx is just equal to b. And so the heat emitted is equal to negative kappa times that cross-sectional area times b. And so now we have 0.15 times 10 to the third is equal to negative 0.5 times 1 times b. And so b is equal to negative 0.30 times 10 to the third. And now for the wall thickness, delta at, for the temperature difference across the wall, we're going to take the temperature at 0.2 minus the temperature at 0. The temperature at a thickness, at the x value of 0.2 is going to be A plus 0.2 times negative 0.3 times 10 to the third. And then at the thickness of 0 at the other end of the wall, we just have A. So those A's cancel out. And we get a change in temperature of 0.2 times this. So negative 0.06 times 10 to the third, 60K. Any questions about that one? That's number one on the energy transfer by heat. Yeah, that's true. Any other questions? Homework questions? Okay. Okay, so here's the first thing I want to do as part of a review. So first law of thermodynamics review. So I want to just start with the first law of thermodynamics, and then little by little, you know, we have all these little equations for how to calculate work, how to calculate heat. But I think the way to think of it is you just have this simple equation that you start with, and then little by little, you know, you can fill in for those, for that simple equation, the more complicated stuff. So first, take a second and do this. Just arrange the change in energy, Q and W, into the first law of thermodynamics. Okay, so the starting point of pretty close to everything that we've done so far is just that the total change in energy is equal to the heat added to the system minus the work done by the system. So now, with that equation, rewrite the first law of thermo so that now you're using the change in kinetic energy, change in potential energy, and the change in internal energy. So now all of those, these are all changes in properties. These are all types of energy of the body. So we'll replace the change in energy with these. You get change in kinetic energy plus change in potential energy plus change in internal energy is equal to Q minus W. And the first two you can rewrite as long as the potential energy we're dealing with is just gravitational. You could write this as like 1/2 times the mass of the system times the velocity at the later instant squared minus the velocity at the earlier instant squared plus mg delta h. Plus we still have this change in internal energy is equal to Q minus W. We still haven't, you know, the only one of these, if you look at the simplest equation, that starting equation, there's only one, sorry, go to the second one instead. So This one that has change in kinetic energy, change in potential, change in internal is equal to Q minus W. There's only one of those terms that we haven't expanded on at all yet, and that's the internal energy. We are going to expand on that, but in order to do that, we have to start talking about gas properties and the ideal gas law and modifications of that. So we haven't done anything with this yet, but everything else we can expand on. And, little by little, this equation is just getting more and more complicated. But we're always just starting with that conservation of energy, Okay, so now, where do these fit in? Skip C. So now rewrite this equation using the integral from volume 1 to volume 2 of PDV and the integral from theta 1 to theta 2 of moment d theta and the integral from x1 to x2 of sigma a dx. So where do those fit in? Okay, so these are all expressions of work. This is the work done by a gas in expansion. This is the work done by a torque in rotation. This is the work done by a rod in tension. And so this equation now, we have the kinetic energy, so 1/2 times the mass times V2 squared minus V1 squared, plus mg times H2 minus H1, plus the change in internal energy, is equal to Q minus, and now the work can be broken up into all these pieces. So you have the work, integral of PDV. You have, depending on the next two, so this can be work that's done on the system or work applied by the system. So I'm going to do both of these as plus minus, just depending on whether the torque is doing work or having work done. But integral from theta 1 to theta 2 of m d theta, bless you. And then the integral from x1 to x2 of sigma a dx. Okay, so that's about as complicated as the I don't know what you would call it, the sort of standard form of the first law of thermodynamics can get. I mean, I guess you could also talk about, we also have ways to expand heat, but when we treat heat, we're always talking about a rate of heat transfer. And so you could do them as time integrals, but let's not do that. Let's take a step now and say, okay, now let's go to the differential form. And the differential form of the first law of thermodynamics is the only place that you're going to work with heat. Okay, so the differential form of the first law says ddt of the energy is equal to q dot minus w dot so now the first thing that we are likely to do with this is, one thing that we would use this form for is if we know that we're in steady state. So no properties of the system are changing. So rewrite this for the case of steady state. For a steady state process. Okay, so if you don't have any changes in the properties, then the time derivative of the energy is 0, and you get a form that looks like 0 is equal to the rate of heat transfer minus the rate of energy transfer by work. And now, the last thing we've done is where do we put the rate of heat that's emitted equal to negative kappa times A times dt dx. And the rate of heat that's emitted is equal to the emissivity times the constant times the area times, well, let's do one that's the temperature to the fourth, or in the special case where we have a body surrounded completely by a larger body, epsilon sigma A times the quantity temperature of the body to the fourth minus temperature of the surroundings to the fourth. And then the last one is the heat emitted, the rate of heat emitted is equal to the constant H times A times the temperature of the body minus the temperature of the surroundings. So now put these three expressions into the steady state equation that we just had before. And so now these all add up to Q dot. And so this equation is 0 is equal to, and we don't know what the signs of any of these are. The sign convention for these heat transfer formulas are different than the sign convention for the first law. So I'm going to write all these as plus or minus kappa A dt dx plus or minus epsilon sigma A times, I'll do the net one, T of the body to the fourth minus T of the surroundings to the fourth plus or minus HA, temperature of the body, minus temperature of the surroundings, and then minus the rate of work. And that's really all we've done with the first law of thermodynamics. I guess if I were going to think of like a algorithm for using it, I would first think, do I have a reason for choosing the standard form or the differential form? You know, is it steady state or am I dealing with heat transfer? If it's steady state or you're dealing with heat transfer or both, then you're going to use the differential form. Otherwise, you're probably going to use the standard form. And then from that point on, you're just going to be making these substitutions based on whatever values you're given. Any questions about that way of thinking about it? Yeah. Mm-hmm. Yeah. That's right. That is not Boltzmann's constant. That's a normal stress. It has the same units as pressure, and you talk about stresses in D form. Yep, that's totally different. Any other questions?
If we wanted to like expand it even more, we could like take the time derivative of those integral expressions for the differential.
Okay, so yeah, yes, you could take all the time derivatives of that standard form, or you could, if you had to put those expressions for rate of heat transfer into the standard form, you'd have to figure out a way to integrate those with respect to time, but then those could go in for Q and the, yeah. But we don't have any problems like that. So it's a simple equation that just sort of keeps expanding. All right. So here's the first question I'd like you to work on together. So let's say that you have like a microchip, a silicon chip, embedded in some medium, so that the only thing that's exposed to the air, or I guess to the coolant in this case, is the top surface. It's embedded in this medium, and you have a coolant flowing over it. The area of top of the chip is 5 millimeters by 5 millimeters. The coefficient for convection is 150 watts per meter squared Kelvin. And the coolant temperature is 20 degrees Celsius. There is work input through electricity. That's the work of displacing charged particles. So the electrical power input is 0.225 watts. And we want to know what's the temperature of the chip. Assuming that this is in steady state. Okay, so before you start working on this, it says it's steady state, and you can tell because it gives you the coefficient for convection. We're going to be talking about heat transfer. So are we going to be using that standard form of the first law or the differential form? Yeah, so it has to be the differential form. So that's your starting point. Okay. Yeah, work on that.